This is an introduction to series solutions of differential equations, and in this video we will be talking about the Taylor polynomial approximation. I will tell you that the Taylor polynomial approximation is probably the best tool or the best numerical method for approximating functions. So basically the Taylor polynomial of degree n centered at x naught, approximating a function f of x possessing n derivatives at x naught, is given by this formula. So you can see here, this is a Taylor polynomial of degree n, and the first term is always going to be the function evaluated at x naught, and then we move forward on to the next term, which is the first derivative of the function evaluated at x naught, multiplied by x minus x naught, and you can see here, that's to the first power, and so forth. This is the second derivative, and that's the second power of that term, and so forth. Okay, this is the 0th derivative here, and this is x minus x naught to the 0 power, which is just 1. So you can see a pattern here very clearly, and we will go all the way to the nth derivative of f evaluated at x naught divided by n factorial. So you can see these factorials match these derivatives and power of that factor. Here we have a nice summarization with sigma notation, and j begins at 0 and goes all the way to n, and we evaluate the jth derivative as j goes from 0 to n, and have the jth power on that x minus x naught term, and then we have j factorial in that denominator. Okay, so let's go ahead and take a quick look at what an estimate of error would be by using this approximation. So if we are using the Taylor polynomial to approximate a function for x near x naught, we measure the accuracy of the approximation as this expression right here. So we have the error occurred by using the Taylor polynomial to approximate the function f of x as epsilon of x. Okay, and there are several formulas for estimating epsilon of x, but the most transparent is due to Lagrange, which states that if the n plus first derivative of f exists and it is continuous on an interval containing x naught and x, then epsilon of x is equal to the n plus 1th derivative of f evaluated at xi divided by n plus 1 factorial multiplied by x minus x naught raised to the n plus 1 power. I do want to kind of mention how you pronounce this Greek letter. I guess it's kind of written like that, and it's pronounced xi. It's kind of an interesting pronunciation. Okay, so and that's where xi is guaranteed. So it's pretty powerful to lie between x naught and x. We may not know exactly what it is, but we know that it's between x naught and x. And we will have one example with this determination of error. And the error is quite simple, because basically it's saying that the actual value of that function at x minus the estimate, or excuse me, the approximated, using, of course, the Taylor polynomial, is equal to the error. So it's quite simple when you look at that. Okay, so let's take a look at our first example. We're going to determine the first three non-zero terms in the Taylor polynomial approximations for the given IVP shown here. The first thing I want to note is that x naught is equal to 0. So that is going to be very helpful for us. We really don't know how many computations we have to make until we know. But what we do know is we are looking for y evaluated at 0 plus y prime of 0 divided by 1 factorial multiplied by x plus y double prime evaluated at 0 divided by 2 factorial multiplied by x squared plus y triple prime evaluated at 0 divided by 3 factorial multiplied by x cubed, and so on and so forth. So we are going to find the first three and we'll know where to stop. So basically, we need to find some of these function values, these derivatives, and then function values. So let's go ahead and make sure we know y of 0 was given to be 1, okay? So now we need to find y prime of x, and of course that's given to us right here. So we could actually just go ahead and plug in 0 there, and we are going to use this equation, of course. So we have 0 squared plus y of 0 squared, and y of 0 squared is just going to be 1 squared, and we have 1 for y prime of 0. So now we are going to need to find some of these derivatives, okay? So we are also going to need to find y double prime. Of course, we'll just take the derivative here implicitly. So we have y double prime of x is equal to 2x plus 2y of x multiplied by y prime of x, okay? And so we can have y double prime evaluated at 0, and you can see that 0 plus 2 times 1 times 1, and we come up with 2. It looks like we're going to have our three terms already. So we can now say that y of 0 is equal to, of course, 1 plus y prime of 0 is equal to 1 divided by 1 factorial multiplied by x. Y double prime is going to be 2 divided by 2 factorial multiplied by x squared, and of course so on and so forth. But now we can say that this is equal to 1 plus, so let's actually label this. So we could say therefore P, and remember we're going to match our n right here, so this is going to be P2 of x is equal to 1 plus x squared. Okay, let's take a look at our next problem. Determine the first three non-zeros again, so our first three non-zero terms in the Taylor polynomial approximations for this given IVP. Again, we see that x naught is going to be equal to 0, and here we have y prime equals the sine of y plus e to the x. Let's go ahead and find y prime. We know y of 0 is equal to 0. Y prime of 0 is the sine of 0 plus e to the 0, and that's equal to 0 plus 1, which is 1. And now we're going to need to find y double prime. I'll just actually do it over to the right here. So y double prime is going to be equal to y prime multiplied by the cosine of y plus e to the x. So evaluating y double prime at 0, we have y prime of 0, which is 1, multiplied by the cosine of 0 plus e to the 0, and we come up with 2. Okay, we are going to need the third derivative. So let's find the third derivative of x. Change that there. Whoops. And that third derivative, we're going to need to use the product rule. So we'll have y double prime. I'm going to do it the other way. And then I will need to have an e to the x. And then we'll evaluate y triple prime at 0. So we have y prime of 0, which is 1. Oh, you know what? Let's simplify this real quick. And this is equal to the opposite of y prime squared multiplied by the sine of y plus y double prime cosine of y plus e to the x. And now we will evaluate this at 0. So y prime of 0 was 1. Multiplied by the sine of 0, which is 0, plus y double prime, which is 2, multiplied by the cosine of 0, which is 1, plus e to the 0. So here we have 3. Okay, so now it looks like we're going to have 3 non-zero terms right away, going all the way to our third derivative. I thought I might write it like this right now. So right now, the Taylor polynomial is equal to y of 0 plus y prime of 0 divided by 1 factorial multiplied by x, y double prime of 0 multiplied by divided by 2 factorial multiplied by x squared, y triple prime evaluated at 0, 3 factorial multiplied by x cubed, and so forth, all the way to that nth term. So now what we'd like is the first 3 terms. So we could write, and we're going to go to third degree, since this first y of 0 is 0, and then we have y prime of 0 is 1, and y double prime of 0 was 2, and y triple prime of 0 was 3. So this is the third degree polynomial that would give us 3 non-zero terms. So basically we will have x plus x squared plus 1/2 x cubed. Okay, let's take a look at our next problem. Determine the first 3 non-zero terms in this Taylor polynomial approximation. for the given IVP. So here we have our equation, and as you can see, we were already given x of 0, x prime of 0. Of course, we know that our x naught is equal to 0, but we are going to need x double prime of 0, x triple prime of 0, and maybe some more, okay? So we do have x prime of 0 to be 0, and that's going to give us a term of 0. So let's see what we need here. Let's first go ahead and write x double prime of t is equal to the opposite of t x of t. Okay, and that's going to help us a little bit. So now if we go ahead and find y triple prime, and let me just move this a little to the right and write since in front of it, then x triple prime of t is going to be which is equal to the opposite of tx prime of t minus x of t. And we can go ahead and just find x triple prime of 0, and that would be the opposite of 0 multiplied by 0 minus 1. And so we come up with a negative 1 for x triple prime of 0. So now let's just keep going. We will have, and I usually like to just put a little line, or I guess I could go over here and write it. We can go ahead and find x, the fourth derivative of our function x, and that's going to be equal to the opposite of t multiplied by the second derivative of x plus that first derivative of x multiplied by negative 1, of course, then minus x prime of t. So that's our derivative, our fourth derivative. And now let's find that fourth derivative evaluated at 0. So we're going to have 0 plus 0 minus 0. So we're going to have that this is equal to 0. So we are going to have to keep going. We're going to need that fifth derivative of x with respect to t. So you can sort of see a little bit of a pattern here. Let's go ahead and see what this is here. So you could see here that this is the opposite of tx double prime of t minus plus 2x prime of t. And with that, we could see a little pattern for the third derivative. If you note this here, I'm going to try one more time. Put it right there. If you notice right here, if we take a negative out, we have a tx prime of t plus x of t. So we see that we have a little pattern here. So when we had the fourth derivative, we have this right here. And there's the second derivative. So we can say that that fifth derivative is the opposite of t multiplied by the third derivative of x plus 3x double prime of t. So let's note the pattern. Okay, and so let's go on to the sixth derivative of t. So we would have the opposite, and this time it would be x, the fourth derivative of x plus 4x triple prime of t, and so on and so forth. Let's go ahead and evaluate this fifth derivative at 0, and as you can see, this first term is going to be 0, but we just need the opposite of 3 times that second derivative. And so I'll just have to move these down separately. See if we can go ahead and plug those in. So that fifth derivative evaluated at 0, you can see that we're going to have I did forget to put this here, that the second derivative evaluated at 0 is going to be 0. And of course, that's because we have the opposite of 0 times 0, and that's equal to 0. Okay, so I should really put these derivatives. There's the second derivative evaluated at 0, the first, the function value at 0. Here's our third derivative evaluated at 0. Here's our fourth derivative evaluated at 0. And we are now working on our fifth derivative. We have seen this pattern here. And if we go ahead and evaluate this, we are going to have 0 plus, and remember x double prime evaluated at 0 is 0, so we have 0 for that fifth derivative evaluated at 0. We are going to need, we have one term here. Let me go to pink. We have one term that has a non-zero coefficient, you could say. Then the first derivative is 0, so that's a no-go. The second is a no-go. We do have the third, so we're going to need one more. We didn't have one here. We didn't have one here. So let's go ahead and evaluate this sixth derivative at 0. And of course, we have 0 plus 4. And then our third derivative was -1. So we come up with a positive 4. So there we have our values of the derivative for our Taylor polynomial. So with all of that, we can say that, and we'll go ahead and name that degree in a minute. So let's go ahead and put a question mark here, and we'll talk about what degree it's going to be. But it will be 1, which is going to be our x of 0. And then we'll need our next non-zero, which was our x triple prime of 0. So that's going to be a minus, and that was a 1 divided by, and that's a third degree term, so this would be t cubed plus, and here is our third, and I'll just go ahead and circle it, value, and that is from the sixth derivative. So we will have 4 divided by 6 factorial multiplied by t to the 6th power. There we have 3 non-zero terms, and as you can see, this is going to be p sub 6 of x. And we can go ahead and simplify that. and we have 1 minus t cubed divided by 6 plus t to the 6th power divided by 180. And there are our first 3 non-zero terms. Okay, let's look at our last example here, and it says determine the first 3 non-zero terms. Again, we're looking for the first 3 non-zero terms in the Taylor polynomial approximations for this IVP. So here is our equation. And as you can see, theta naught is going to be equal to 0. And we're given our function value, our initial conditions. We have 0, and we have 0 for the function value at 0 and the first derivative evaluated at 0. So we are going to have to be looking for some derivatives. Let's go ahead and rewrite y double prime of theta is equal to the opposite of y of theta all cubed plus the sine of theta. So now we will evaluate y double prime at 0, and we have the opposite of y of 0 cubed plus the sine of 0, and that's equal to 0. So now, just so that we can keep track of these, whoops, I'll do those in yellow. So we have our function value, our first derivative, and our second derivative evaluated at 0 to be equal to 0. Let's go ahead and find our third derivative. So we have y triple prime of theta is going to be equal to negative 3y of theta squared multiplied by y prime of theta plus the cosine of theta. And we can evaluate y triple prime at 0, and you can see that we have negative 3 multiplied by 0 and 0 plus the cosine of 0, and we come up with 1. We'll go ahead and find that fourth derivative of theta, and that's equal to okay, and so now we can go ahead and evaluate that fourth derivative at 0. And as you can see, we're going to have 0 plus 0 minus 0. So that fourth derivative is going to be equal to 0. So moving forward with these next derivatives, I will leave that up to you to go ahead and find. So we do have the fifth derivative of y at theta to be the opposite of y of theta cubed. And I hadn't been really putting that. And we were taking that derivative minus the cosine of theta. So we do see a little bit of a pattern here. And I guess the pattern is that the sixth derivative evaluated at theta is going to be equal to the opposite of y of theta cubed. Actually, this was supposed to be the third derivative, and this will be the fourth derivative plus the sine of theta. We'll follow along with that pattern. The seventh derivative evaluated at theta is the opposite of y of theta all cubed, and that would be the fifth derivative plus the cosine of theta. We should be good. Let's go ahead and find the fifth derivative evaluated at 0, and we would have the opposite of the cosine of 0, which is equal to -1. Here, the sixth derivative evaluated at 0 will have the opposite of the sine of 0, and we do have 0. Here we have the seventh derivative evaluated at 0, and we will have a positive cosine of 0, which is equal to 1. So we do have some of these values, and hopefully we'll have 3. Here's 1, here's 1, here's 2, and here is 3. So now we can go ahead and write our first 3 non-zero terms, and as you can see, we're going to be the seventh degree term, and we will first have our y triple prime of 0, which is 1 divided by 3 factorial multiplied by theta cubed minus, now we'll work on this one, which will be a 1 divided by 5 factorial multiplied by theta to the 5th, plus there's a positive 1 over 7 factorial multiplied by theta to the 7th power. And if you'd like, we can go ahead and compute these. This would be 1/6 theta cubed minus 1/120th theta to the 5th plus 1 divided by 5040 theta to the 7th. And those are our first 3 terms. Now, those were our examples in finding the first 3 non-zero terms. Let's go ahead and look at an example that talks about this error that we make by approximating with a Taylor polynomial. So let's just start coming up with some of our derivatives. So we started with f of x equals ln of x. And by the way, our x naught is equal to 1 because of this statement. We're looking for approximations close to 1. So f of x equals ln of x. And so we'll have f of 1 is the natural log of 1, which is 0. So we'll have f prime of x, which is 1 divided by x, and f prime of 1 is equal to 1. F double prime of x is going to be the opposite of 1 over x squared, and f double prime of 1 is -1. And then we can find f triple prime of x, and we're going to have 2 divided by x cubed. And we'll evaluate that third derivative at 1, and that will be equal to 2. So what we have is P3 of x equal to 0 plus 1 over 1 factorial. Whoops, I'm going to have to write this below because we have x naught equal to 1. So we will have those factors. So therefore, P3 of x is going to be 0. That's our f of 1 term, plus 1 divided by 1 factorial multiplied by x minus 1, minus 1 divided by 2 factorial multiplied by x minus 1 squared plus 2 divided by 3 factorial multiplied by x minus 1 cubed. So what we end up with is x minus 1 minus x minus 1 squared over 2 plus x minus 1 cubed over 3. Okay, so now we're going to apply the error formula. But first we're going to go ahead and compute the next term. So we're going to find the fourth derivative. And that will be the derivative of the third derivative, of course. And that will be the derivative of 2 over x cubed, that derivative. And of course, we come up with negative 6 over x to the fourth power. So now let's talk about our error. This is going to be the error that we have after approximating the function ln of x using a third degree Taylor polynomial. So we have epsilon of x, and it has a subscript of 3 because we are approximating it with a third degree polynomial. So here we have the natural log of x, which is our function, minus that third degree polynomial that we have up there. So that is going to be equal to the fourth derivative evaluated at xi divided by 4 factorial multiplied by x minus x naught to the fourth power. So it's really important that we see that the error that we made using a third degree polynomial uses the fourth derivative to find this error, okay? So let's keep going. So now we have that this is equal to, and let's put that fourth derivative in there. So we have the fourth derivative here evaluated at xi is equal to negative 6 divided by xi to the fourth power. Okay, so let's go ahead and put that in there. We have a negative 6 divided by 4 factorial is 24. And here we'll have our xi to the fourth power. Then we'll multiply by x minus 1 to the fourth power, and we come up with the opposite of x minus 1 to the fourth power divided by 4 xi. Try that one more time. To the fourth power. Okay, see if I can make that just a touch smaller so we can fit that in there. Okie dokie. So now let's go ahead and see what we have. They've asked us to estimate what we have here. Actually, that was part C. They've asked us here to use the error formula to show that the absolute value of the natural log of 1.5 minus the third degree Taylor polynomial evaluated at 1.5, that absolute value is equal to the absolute value. We're going to use this right here. the absolute value of the opposite, of 1.5 minus 1 to the fourth power, all divided by 4 cos to the fourth power. And that's equal to 0.5 to the fourth power divided by 4 cos to the fourth power. And we know that that is less than or equal to 0.5 to the fourth power divided by 4. Of course, that's because we know that cos is greater than 1. And so now with that, we know that this is equal to, put that in your calculator, 0.015625. Okay, in part C, what we're going to do is compare our estimate with the actual error. So basically what we can do, some direct calculations. We have that the absolute value of the natural log of 1.5 minus our third degree Taylor polynomial that we use to approximate the natural log of x is approximately equal to, and I just put ln of x in the calculator, and we have 0.405465 minus, and here's our third degree Taylor approximation, evaluated at 0.5. So we have 0.5 minus 0.5 squared divided by 2 plus 0.5 cubed divided by 3. Now, as you can see here, our third degree Taylor polynomial, we subtract 1 from 1.5. So I will just go ahead and write that in here. So this is 1.5 minus 1. Okay, because that was x minus 1. Okay, and so if you compute that, you will come up with approximately 0.011202. So pretty close. And in part D, you can go ahead and use your calculator. And of course, y1 of x, you can go ahead and use ln of x, and y2 of x. You can go ahead and put our P3 of x in your calculator. And that P3 of x we have right here. X minus 1, so it'd be very, very easy. So we have x minus 1 minus 1/2 x minus 2 squared plus 1/3 x minus 1 cubed. Okay, so you can put those in your calculator. And you will see, of course, that natural log function. And then, of course, the approximation. Now, I'm just going to go ahead and really just kind of use a dashed line in here. But it's kind of like this. And then it kind of comes around and curves up. So it kind of follows along this, and then it gives a little curve up, and it's going to look a lot like that, okay? So you'll be able to see both of those in your calculator. And you do want to take a look at them between 0 and 2. This is about 2. Of course, I didn't draw that very good because this is where 1 is. So I'd have to really scrunch this up, and I don't want to do that. But anyway, so you'll get an idea of what those look like. I could probably move this over a little bit. That would be a little bit better. And you could see that, whoops, that's where 1 is. And so this other function comes about like this. Okay, so that concludes this lesson.